final things which we need to look at in this segment. So before starting Planck's approach, we saw that Wien came up with one expression and Rayleigh-Jeans came up with one expression. We saw that Wien's approximations, wait, I'll show you the slide. Yeah, so Wien's expressions worked for short wavelengths but not for long wavelengths. Rayleigh-Jeans worked for long wavelengths but failed at short wavelengths. This is what we saw. And then Planck came and gave this expression. So we are now going to test to see if this works both at short as well as long wavelengths. So first we'll see at short wavelengths. If the wavelength is very short, it means frequency is very high, because product of wavelength and frequency is a constant. So if nu is very high, then this entire term e to the power h nu by kt is going to be very high. So you sort of ignore this minus 1 term. So it becomes 8 pi h nu cubed upon c cube 1 by e to the power h nu by kt dv. What are we doing? Because nu is very high. Okay, wait, we're talking about short wavelengths. If lambda is very small, then nu is going to be very high because their product is a constant. So because nu is very high, this term is going to be a very big number. So subtracting 1 or not subtracting 1 is not going to make a huge difference. So we ignore this minus 1, we just make it 1 by e to the power h nu by kt dv. Now we're going to bring nu in terms of lambda. Nu is equal to c by lambda and d nu equals c by lambda square d lambda. So wherever you have nu, you substitute it with c by lambda, and wherever you have d nu, you substitute with c by lambda square d lambda. Then this is the expression you get. Why are we doing this? Because at short wavelengths, Wien's expression worked. So if this works, it has to tie up with Wien's expression. And Wien's expression said that energy is equal to some constant lambda raised to minus 5 e to the power minus c2 by lambda t. So again here, when you do the appropriate substitutions, you will get 8 pi hc lambda raised to minus 5 e to the power minus hc by k lambda t d lambda, which is again c1 lambda raised to minus 5 e to the power minus c2 by lambda t d lambda, where c1 is this constant 8 pi hc and c2 is hc by k. So we can see that this expression which Planck came up with, this one matches with Wien's approximations at short wavelengths. So it holds true for short wavelengths.